This is the brief on hyperbolic coordinate systems. So what we're doing here is unpacking the math framework for systems governed by invariance. And this isn't just abstract theory. It's the exact language needed to solve problems in special relativity and fluid dynamics. First up, parametrization. Instead of drowning in algebra, just think of it as using an exponential map to create a hyperbolic grid. The main goal? Finding the inverse transformation. We're not just plotting points, we're building a two-way map to translate any location back to its original values. Second, the geometry. We need to see if it holds up. We calculate tangent vectors to understand how the grid stretches. But the crucial question is orthogonality. Do the coordinate lines meet at perfect right angles? If they do, it makes the math for complex physical calculations way simpler down the line. And finally, this is where it gets really applied. This geometry powers four major physical applications. In special relativity, it describes Lorentz boosts as hyperbolic rotations that preserve the spacetime interval. It's also the engine behind navigation like Lorentz and acoustic localization. And in fluid dynamics, these coordinates align perfectly with how liquid flows around corners, simplifying tough boundary problems. So whenever physical processes depend on hyperbolic symmetries, like the speed of light or streamline curvature, this system provides the most efficient language for analysis. That's the geometry of invariance.